Good morning, students. We'll start with our today's lecture. So today's lecture is chapter 2. Here it is 3, but it's chapter 2 of unit 1. So there are two parts again in chapter 2, that is transformation and direct x. So direct x I had taught you earlier. So transformation was remaining. We'll complete that today. So transformation is used to scale, translate, rotate, reflect, shear shapes and objects, to change the rotation, make the reflection, translate into another axis, or shear the shapes, that is enlarge or make it unfit or change the objects, is done by transformation. Scaling is again changing it into some direction, is called as scaling. Although algebra is basic notation for transformation, so algebraic expression could be a basic notation to identify transformation. It is possible to express them as matrices. So usually transformation are also identified using matrices, which provide certain advantages for viewing the transformation and for interfacing to various types of computer graphic hardware. So to view them into a particular computer graphic animation world, or to make it compatible with the computer graphic hardware, we require transformation. So 2D transformations have translation transformation, scaling transformation, reflection transformation, 2D shearing, 2D shearing, 2D rotation, 2D rotation, that is converting them into shearing process and into rotation process. So these are the types in your transformation process in 2D. So first we'll be going with the translation transformation. So in translation transformation, the relationship here is 1 to 1. The 1 to 1 relationship between the number and the shape is provided by the Cartesian coordinate, and the relationship is given in such a way that x dash is equal to x plus t of x, y dash is equal to y plus t of y, the algebraic and matrix notation for 2D translation. And using matrices, it will be x dash y dash 1 is equal to 1 0 0 0 1 0 tx ty 1 into that dot product is multiplication x, y and 1. So this denotes your 2D translation algebraic method. Now that is just algebraic method, and this is matrices notation. Scaling transformation. Now what is scaling? You can obtain a scaled object, that is a increased size object, means my actual object is smaller. When I'm scaling it, that is I'm increasing the size, I'm scaling the object. And when I'm scaling the object, I'm making it 2 times, 3 times, 4 times bigger than the actual object. And how do I do that? So to do that, I suppose if I have x dash, that is I have value 6. When I'm scaling it, I'm doing it 2x, right? So what I'm doing, I'm increasing it by 2 variables. So 2 into 6 is 12. This is just a normal example. It's not actually implemented here. The algebraic and matrix notation for 2D scaling is x dash s x of x, y dash is sy of y. So these are the two refractions which are calculated using a 2D scaling transformation. For matrices, it is x dash y dash 1 x s s x 0 0 0 s y 0 0 0 1 dot, that is multiplied by x y 1, that is the opposite of x dash y dash 1. The scaling action is relative to the origin, that is at the point 0 comma 0 remains 0 comma 0. All other points move away from the origin. To scale relative to another point, p of x comma p of y, we first subtract p of x, p of y from xy respectively. This effect translates the reference point p of x, p of y back to the origin. Second, we perform the scaling operation. And third, add p of x, p of y back to xy respectively to compensate the original subtraction. Algebraically, this is. So what do? To scale the object, they subtract the actual object from the scaled one. Then to show the original image, they again add the object so that it should look like a scaled object, that is the larger one. So how do they do that? The first is subtracting x p of x, y p of y from sx and sy, and once they get, that is determinant 7.25, the equation what they get, then they simplify p of x value into the equation, that is 1 minus s of x and 1 minus s of y, and then by combining both these they get the matrices as x dash y dash 1, s of x 0 0 0, s of y 0, p of x 1 minus s of x, p of y 1 minus s of y 1 into x y 1. So this is the matrices they are getting, that is homogeneous matrix form of both the equations combined together, that is 7.27. Next is a reflection. What is reflection? An exact opposite image of my actual image, that is called as reflection. So reflection of the shape relative to y-axis is created by reversing the sign of the x coordinate. Means, suppose if I am standing in front of a mirror, what I am getting is my actual reflection. But the reflection what I am getting is the opposite of my actual image. So suppose my value of my actual object is 6. When I am making it a reflection on the other side of my axis, I am making the denotions of the coordinates also, that is I am making it opposite. That is the reason if my actual value is 6, I am getting the answer in reflection as minus 6. So this is basically 2D reflection. How do they apply it? That is, if I matrix notation for reflecting is, so for an example, if I take x dash is equal to, reflection will be minus x, that is the opposite of x dash. The matrix notation for reflecting about the y-axis is x dash y dash 1 is equal to minus 1 0 0 0 1 0 0 0 1 into x y 1, and for the x-axis it is x dash y dash 1. So see here, only the matrices, first matrices is changing. Minus 1 was in the first matrice, first column, and in x-axis the matrices minus 1 is in the second column, second row. So this is the reflection changing when you change axis to axis also. However, to make a reflection about an arbitrary vertical or horizontal axis, we need to introduce some more algebraic deception. For example, to make a reflection about the vertical axis x is equal to 1, we subtract 1 from the x coordinate. This effectively makes x is equal to 1 axis coincident with the major y-axis. Next, we perform the reflection by reversing the sign of the modified. What do? They subtract some value of x from 1, and then they get some coincident same value which should interconnect to y-axis, and by reversing the signs they change the axis. Now in 2D, how to change the axis? Now to change the axis, what they have to do is, figure below shows the point P of x comma y relative to the xy axis, but we require to know the coordinates relative to the xy axis. So what are the coordinates which are relative to xy axis? To do this, we need to know the relationship between two coordinate system, and ideally we want to apply a technique that works in 2D and 3D. So to scale it, what do? See here, P of x comma y is equal to P dash x dash comma y dash, and here x dash means an extension of time taken in between y axis, and this is extension of time taken over y axis. So this is x dash which is parallel to x, and this is y dash which is parallel to y. So this is basically an operation which is being carried out over the x and y axis. How to change the axis? If the second coordinate system is simple, translation t of x comma t of y relative to the reference system, As shown in figure below, the point P of x has coordinates relative to the translated system x minus t of x in comma y minus t of y. So this is the bifurcation which is made over t of x comma t of y using the translation of simple translation, that is t of x comma t of y over the time taken parallel to the x and y axis. So this is the matrix form which has been formed: x dash y dash 1 1 0 0 0 1 0 minus t of x minus t of y 1 into x y 1. So here x dash and y dash are the axis rotated. So these are the axes which are rotated over the reflection relative to normal x and y axis, as shown in the figure 7.16, that is the prior first one. The transformation product x dash and y dash is relative to the rotated axis. So here cos minus beta is 1, so they have applied 1. Cos minus beta is again 1. Minus sine beta minus beta is 0. Sine minus beta is again 0. So these are the values which are put and which are simplified, which we get in the determinant 7.73. And this is what is the transformation they get over the rotation which is being performed over the beta axis. That is, suppose I rotate the image in this direction, I get the actual image is this one, and I get a rotated image like this over the matrices using the matrices which is being formed in 7.73. With this, we'll stop here for this topic. We'll continue the next topic in the next lecture. Thank you.